Right, welcome back. We are doing Thermodynamics Homework Solutions. This is homework number 7. Homework 7 is on basic entropy calculations, not actual second law analysis, just, calculate the difference in entropy for different things. Okay? And also some conceptual aspects of entropy. So this first one says, what is the change in entropy for heating steam at 10 kPa from 400 to 500? So we've got 400 to 500 degrees Celsius, 10 kPa, okay, and we're steam. Okay. And then it's asking for the same thing from 500 to 600. Okay. And then it is saying, first calculate the change assuming a constant heat capacity, then use a temperature-dependent heat capacity, then use the steam tables. Okay. So basically we're calculating the difference in steam, either as an ideal gas or as steam, with a constant heat capacity or a non-constant heat capacity. Okay, so pretty straightforward. The main thing is to show how different these can be. That kind of, Now, when we did a similar problem like this for enthalpy, we found, at least for an ideal gas, that they were the same because it really was pretty much the same. But we're going to see here that the way the math works for entropy, it's not going to be really exactly the same. So let's do these all in turn. Okay. So first, let's treat this as a full, full steam, as true steam, which means we go to the steam tables. Okay. And 10 kPa is not saturated, so you go to 10 kPa, and so in terms of work, okay, so this is how we'll do it. We'll say like at T, so all at P equals 10 kPa, but we have at T equals 400, 500, and 600, and then we have S equals all its different things. Okay, and so we have 9.6076, 9.8977, and then 10.1608 in terms of kilojoules per kilogram K. Now we just take the difference, okay? So the difference between the first and the second one is going to be about, about 0.28, 29. Okay, so this one's going to be about, delta S1 is going to be about 0.29 kilojoules per kilogram K, and then between those two, it's going to be about, 27, so 0.27 kilojoules per kilogram K. Okay. But that's all it is. It's just, look up the values, take the difference. Now, obviously, it becomes a little different if we have an ideal gas. Now, if we have an ideal gas, then we have to use the ideal gas formula. Okay, but remember there's two of them, so let's write down both of them. Okay, so I have delta S of an ideal gas is equal to Cp over T dt minus R natural log of P2 over P1, or Cv over T dt plus R natural log of V2 over V1. Which one I use depends upon what I have. Now in this case, do I have volumes or do I have pressures? That's right, I have pressure, so I'm going to use the top one. Now the first case says, okay, assume heat capacity's constant. Okay? And so when I do that, okay, I'm going to have delta S of an ideal gas is equal to, Cp over T dt minus R natural log of P2 over P1. This is going to equal Cp natural log of T2 over T1 minus R natural log of P2 over P1. Okay. So, and then I'm just going to plug things in. Okay. Now the thing to note here, though, is that these are in degrees Celsius. I repeat, I cannot use degrees Celsius in this formula. See, when you're doing enthalpy, it becomes Cp T2 minus T1. This one's okay because you have a difference. But because these are degrees Celsius, I no longer can do that. So, yeah, the difference is 100 in both cases. Okay, but the ratio is not the same. 500 divided by 400 is not the same as 600 divided by 500. But more importantly, 673.15, 773.15, the ratio between this one and this one is not the same as this one and this one. Okay, and so the math becomes different. Now this one's going to go to 0 because the pressure's the same. Okay, and it's going to go to 0 actually in both cases. Now in the other case where I have a temperature-dependent Cp, I still have to use Kelvin, but the math is a little bit different. That's S ideal gas equals Cp over T dt. Still this, but that's going to be 0. And so this becomes, R, because it's always multiplied by R, A over T plus BT over T plus D over T squared over T. Okay. Which is equal to, A over T plus B plus D over T cubed. Okay. R. And then that, I just do I do my integral, which is straightforward enough, and that becomes, R times the quantity A natural log of T2 over T1 plus B T2 minus T1 minus D over 2, 1 over T2 squared minus 1 over T1 squared. Again, everything has to be in Kelvin. The other thing that we have to point out is this guy, okay? Now when we do the integral, it's not 1 over delta T squared, it's delta 1 over T squared. That 1 over T2 squared minus T1 squared is not the same as 1 over T2 squared minus 1 over T1 squared. There is a difference between those, okay? And again, at this point, I would just plug in numbers and see how different things are. But that's the main, main aspect of the problems and the main procedure of the problems.